Hello AP Chem students and welcome to topic 2.7, VSEPR and hybridization. The learning objectives for today are 2.7.a, based on the relationship between Lewis diagrams, VSEPR theory, bond orders, and bond polarities. A, explain structural properties of molecules, and B, explain electron properties of molecules. So let's get into this. This has the potential to be a long section, so we're going to see if we can get through this as quickly as we can, but I want to make sure that you still understand. So VSEPR stands for valence shell electron pair repulsion. The main determining factor of the VSEPR theory is that the structure of the molecule arranges itself so as to minimize electron repulsions. In order to do this, both bonding and non-bonding pairs must be considered. So remember, we're considering pairs of electrons. So we're going to fill in some tables here. So this is the main group geometries, which is when all the electron groups are bonds. So in other words, you have no lone pairs on your central atom. Of course, you're going to fill your outer atoms with lone pairs. But in VSEPR, we're mainly talking about the geometry around the central atom. So if you have two electron groups, then there would be two bonds and the geometry would be linear. The bond angle would be 180 and it would look like this. If you have three electron groups, your number of bonds is 3, your geometry is trigonal planar. Bond angle 120, drawing looks like this, like a triangle. If you have 4 bonds, then that's called tetrahedral. And your bond angle here becomes a little bit something that maybe you didn't expect. It's 109.5, and that's because of the three-dimensional arrangement of tetrahedral. So linear and trigonal planar were both planar, so they're in just a flat plane like this. Once you get to tetrahedral, you get that three-dimensional shape, and that's where you get this 109.5. If you have 5 bonds, that's trigonal bipyramidal, and you have 2 bond angles here, 120 and 90. So you can see that around the center of this shape, you've got a triangle, which is the 120, and then the 90 is there's like a linear top and bottom. So you got a triangle and then a linear. And so that's where you get these 2 bond angles here. And then for 6 bonds, it's octahedral, bond angles of 90, and you can see that. I'm going to strongly recommend, if you have not already, that you visit the molecule shapes FET, because that's going to really help you start to see these and visualize these three-dimensionally. A modeling kit is also a great resource if you have access to that. Now, once we start thinking about pairs that are non-bonding, so in other words, lone pairs, you need to remember that they still take up space in the molecule, so they're still contributing repulsion to the structure. So here's a trigonal planar situation where you have 3 electron pairs that are all bonding. But you can see there that if we swap one of these for a non-bonding pair, they are still taking up space in the atom. And so then this bond angle of 120 is maintained because this electron pair is repulsing. So when considering, a molecule with multiple bonds in the VSEPR theory, you should be aware the multiple bonds count as one effective electron group. So even though we actually, have more than one pair that we're considering here, we think about it as electron groups. Okay, so if you have 2 bonds and 1 lone pair, your geometry is going to be bent, and the bond angle there is 120, and it looks like that. If you have 3 bonds and then 1 lone pair for a number of electron groups is 4, the geometry is trigonal pyramidal. So what you got here is your core, your base geometry is tetrahedral, but you're replacing one of the lone pairs, one of the bonds with a lone pair, and so then you get this bond angle that's going to be close to 109.5. It's actually going to be a little bit less, and I'll show you that in just a minute. So there you go. And then if you have 2 bonds and 2 lone pairs, that geometry is called bent, okay, again, but it's got a different bond angle. This one is again slightly less than 109.5. So we're going to talk about that. Now, I do want you to know you cannot just say less than 109.5 like this. You need to say like slightly less or between 100 and 109.5, because if you just say less than 109.5, that could be anything down to 0. So you do need to be specific. So saying something like slightly less than 109.5 is probably good. So then this pattern continues. So then when we've got 5 electron groups, we gradually replace the bonds with lone pairs. So here's 4 bonds, 1 lone pair. That becomes seesaw. Your bond angle here is going to be 180 across the top. And then you're going to have a situation down here where you've got some 90s going on and then a 120 there. If you have 3 bonds, 1 and 2 lone pairs, that becomes something we call T-shape. And then we can actually get all the way back to linear. So if we have 2 bonds and 3 lone pairs, we lose that whole triangle situation around the trigonal bipyramidal, and you come back to linear with 180. When you have 6 electron groups, if one of them is a lone pair, that becomes something we call square pyramidal with slightly less than 90. And then if you have 2 lone pairs, then we come to something called square planar. So back to kind of a planar situation because we lose that linear part in the middle of the octahedral. All right, so then let's think about polar versus nonpolar molecules. So we've already talked about polar and nonpolar bonds. It's important to realize then that when those bonds come together into a molecule, then they can create a polar or nonpolar molecule. So a lone pair actually repels bonds more than another bond will, as we were just talking about. And so then the bond angle, if the bond angle is more than 120, the lone pairs have enough space, and then you don't see distortion. But with bond angles that are less than 120, you do see the distortions, okay? So for example, here's methane. This has got all bonding pairs, and so you see our ideal bond angle 109.5. If we replace one of the bonds for one lone pair, you see that we get some distortion to 107.8. And if you replace with 2 lone pairs, we get even more distortion with 104.5. You do not need to memorize these bond angles. You do need to know that they are slightly less than 109.5. Again, saying a range like, you know, around 105 or close to 109 or something like that is going to be just fine. But please don't just say less than 109.5 because that opens up the whole range. You have to be very specific. Okay. So keep in mind your strength of your repulsions. Your lone pair repulsions are stronger than lone pair bonding pair repulsions, which are stronger than bonding pair repulsions. And that's kind of what we see set up here with these diagrams. So then continuing with this idea of polar versus nonpolar molecules, Lewis structures allow us to determine if a molecule has a dipole moment or is polar. So a polar molecule is a molecule that has an area of partial positive charge on one side, while the other side is an area of partial negative charge. This happens when polar bonds exist in a molecule that do not cancel each other out, or if you have an uneven distribution of electrons for another reason. We're going to look at those situations. And this creates what we call a dipole moment. Now, we have a symbol for that. This is a lowercase mu, which you can see there. Okay, so here we've got 2 polar bonds. The CO bond is polar, but you can see that in terms of the VSEPR theory, the geometry is evenly distributed, so those bond dipoles are going to cancel each other out because they're pulling in opposite directions, and so then they cancel. Think about a tug of war. If this was a tug of war, that flag would stay in the middle. So no net dipole moment. However, when we have 2 lone pairs here, like we do in water, those are not shown in this picture, that causes this bent arrangement, and so it comes down like that. And so then these bond dipoles between hydrogen and oxygen no longer cancel. And so then what you see is that you have more electron density on the oxygen than you do on the hydrogen, and that does create a dipole moment. And we indicate that with this arrow with a plus at the end. So the arrow points to the negative end of the molecule, and then you put this little plus on the tail to indicate the positive side, the partial positive side of the molecule. So this has what we call a net dipole moment. So there's some steps that you can think about to determine if a molecule is a dipole moment. So number 1, think about the polarity of the individual bonds. So for example, for water, the OH bond is polar, and then we think about the geometry of the molecule using VSEPR. So in this case, we have bent geometry, so your bond dipoles are not going to cancel out, and therefore this is going to be a polar molecule. However, if we think about another situation with methane, we have the CH bond, which is nonpolar covalent, and the geometry is tetrahedral, so it's an even distribution anyway, and so then that creates a nonpolar molecule. Now let's look at a situation, again, we already kind of talked about this with carbon dioxide. We do have a polar covalent bond, but we have a linear geometry, and so the VSEPR geometry is going to have those bonds evenly distributed. They are going to cancel each other out, and you're not going to have a dipole moment because this is going to be a non-polar molecule. So just to show you a few more examples here, here are some examples of polar molecules. And you can see in all of these that we have bond dipoles that do not cancel out. Versus the nonpolar molecules, these bonds have dipole moments, but overall their geometry is evenly distributed, and so you're not going to see a dipole moment. I do want to specifically show you ozone, because ozone you might expect to be nonpolar because this bond is nonpolar. However, you have an uneven distribution of electrons here in the ozone molecule because of the way formal charges are set up. So if you remember formal charges from the last section, we have uneven distribution of charge in this molecule, and so this is polar. I would not expect you to have to know necessarily that ozone is polar, but they would want you to be able to explain why it is. And so they would probably give you a situation where they would say this molecule is polar, justify this based on formal charge or something like that. Okay, so here's some examples for you to think about. So determine if the following molecules are polar or nonpolar. So I'm going to pause the video. If you want to go ahead and try this and pause the video, I'm going to go through the answer in just a minute. Okay, so we're going to look at PF3 and PF5. So do they have polar bonds? And then the answer for PF3 is yes, it does. What is the VSEPR? Trigonal pyramidal, which is an uneven distribution of bonds. Does it have a dipole moment? And the answer is yes. The reason for this is that you have 2 lone pairs on your phosphorus here. And so this creates that, I guess 1 lone pair on phosphorus here, which creates trigonal pyramidal. And so, yeah, there we go. And that's your uneven distribution of bonds. Then for PF5, on the other hand, though, we still have those polar bonds, but it's trigonal bipyramidal with an even distribution of bonds. Therefore, it would have no dipole moment. All right, so let's talk about the valence bond theory. So the valence bond theory describes a covalent bond by thinking about the shape of the orbitals that were overlap in order to form the bond. So remember that a bond is really just electrons that are sharing the same space in between the 2 atoms, okay? So with valence bond theory, it defines a covalent bond as saying that it's formed by the pairing of 2 electrons with opposite spins, so 1 spin up and 1 spin down. You remember talking about the arrows before, in the area of orbital overlap between the 2 atoms. This area of overlap has a high electron charge density. So remember that an orbital is just the area in which an electron is likely to be found. And so this is just talking about like they're close enough together that electrons from here and electrons from here are going to be able to occupy the same space. So this is what that looks like. So if you have an H on its own, you have 2 H's and they come closer together. And then eventually they come close enough together that the area in which they're likely to be found overlaps, and we call that a bond. That's an electron pair bond. So it goes from being an up and an up to being an up down. So don't need to know that graphic, but I thought it might help you to understand. Here's what you do need to remember about the valence bond theory. Thing 1, bonding electrons are in the area of overlap, which is the greatest probability of finding a bonding pair, okay? For orbitals with directional lobes. So directional lobes are things like the s orbital does not have a directional lobe. It's a sphere. You can turn it all around. It looks the same. But P, D, and F have those lobes where they've kind of got an oblong shape. So if you turn them, you can see a difference in orientation. So in that case, maximum overlap occurs when the atomic orbitals overlap end to end. So like in a straight line like this. So the molecular geometry depends on the relationships among the central atom orbitals. Let me show you. So in examining atoms, the expected geometries from the orbitals that participate in bonding do not always match the experimental and VSEPR theory angles. So to account for this, that's where we come up with this blending of the native orbitals to create special hybrid orbitals. And that's what we call hybridization. It's important to realize this is hypothetical, not observed, but it does fit the data. And so it is a model that we're working with. Okay, so for example, if you have 1 s orbital and 3 2p orbitals, so this is what it looks like to begin with. So 1 of these and then 3 of these, they hybridize and then form this kind of like, like exclamation mark situation. So you start with 1 sphere and 3 of these kind of propeller looking things, and then they come together to give this kind of exclamation mark situation. And so then they would overlap to give this situation. I'd like that to move again, all right? So then that's what a hybrid orbital looks like. So these hybrid orbitals can be occupied by either bonds or lone pairs. A multiple bond only occupies 1 hybrid orbital. So in all of these bonding situations, we treat multiple bonds in the same way that we would treat a single bond. So it doesn't matter if you have a single, double, or triple. They're all treated the same when you're thinking about molecule geometry. Okay, so then let's talk through some of these hybridizations here. So with sp3 hybridization, you have 4 electron groups. Hello, clicky, click, click, click. Oh, hang on. There we go. You have 4 electron groups that are coming from 4 orbitals. So 1s and 3p. So 1, 2, 3, 4. So you can see if we add the exponents, you get that 4 there, right? 1s and 3p. So that forms 4 hybrid orbitals with a geometry of tetrahedral. So the geometries of your VSEPR match the VSEPR geometries for that number of electron groups when we thought about the electron group geometry. So then your bond angles are also the same, so 109.5. So nothing new to like memorize here except this idea of sp3 and then it's hybridized, all right? And then here we're treating, again, lone pairs, bonds, and multiple bonds are all treated the same. Okay, so then sp2 hybridization, you have 3 electron groups that are formed by the hybridization of 1s and 2p, forming 3 hybrid orbitals with trigonal planar geometry and bond angles of 120. And then finally, sp hybridization, you have 2 electron groups that come from 1s and 1p that are forming 2 hybrid orbitals with a linear geometry and bond angles of 180. Now, if you go online, or you may remember from honors that we have these other 2 hybridized orbitals, so dsp3 and d2sp3, which also corresponds to trigonal bipyramidal and octahedral. Those have been excluded from AP content, so you will not need to know those for the AP exam. So then covalent bonds and hybrid orbitals are given special names because of the way that they overlap. So covalent bonds formed by the overlap of the end-to-end hybridization like that is called a sigma bond. Yes, I know. Okay, and so then the symbol for that is lowercase sigma. All single bonds and the first bond of a multiple bond are sigma bonds. Bonds formed by the parallel overlap of unhybridized orbitals are called a pi bond. So all multiple bonds are pi bonds. Because there is more overlap in a, so here, we're going to show you this. So here's a sigma bond. So if you have ethane, so here's your sigma bond here in the middle between your carbon-carbon, right? And then you're going to have, so we've got 1, 2, 3 hybrid orbitals here, all right? But then that leaves behind an unhybridized orbital, okay? Because from carbon, you would expect it to have 1s and 3p. So we've not used one of the p orbitals. Those p orbitals overlap and form what's called a pi bond. And so then that's your double bond. Now, it's important to notice that there is a top and bottom part of the pi bond. That is just one pi bond. That's top-bottom situation. Okay, so a single bond is made up of 1 sigma bond, a double bond is made up of 1 sigma and 1 pi, and a triple bond is made up of 1 sigma and 2 pi. All you need to be able to do here is count the number of sigma bonds and the number of pi bonds. If this is a little bit foreign to you, that's okay. I just need you to be able to count the number of sigma and pi bonds in a molecule in total. So because there's more overlap in a sigma bond than a pi bond, the sigma bond is a stronger bond with a greater bond energy than a pi bond if we're pulling those apart individually. However, you might remember that in total, a sigma bond is longer and weaker than a double bond, which is longer and weaker than a triple bond. Okay, so do keep that in mind. All right, so finally I want to talk about geometric isomers. So the structure of a pi bond restricts the rotation, right? So when you just have this sigma bond overlapping like that, things can spin. But as soon as you have this pi bond kind of going top and bottom, that kind of makes it rigid. So those can't spin against each other, and so then that's in place. So that sets up what we call a geometric isomer. So an isomer has the same number of atoms and types of bonds, but differs in the bond placement. And we commonly see this across a double bond. So 2 kinds of possible isomers that you should know about are cis and trans. And so these might be prefixes that are familiar to you. So cis means same. So what we have here is a cis but2ene, which means that these groups, the CH3 groups, are on the same side of the double bond, versus trans. So trans means opposite. And so then here the groups are opposite. So you can see here they're on the same side and here they're on opposite sides, okay? Same thing down here. We have these ammonia groups cis, and then here they're trans. And then here these methyl groups here are cis, and here they're trans. All right, so that's it for the video. So there's a lot, again, to go through in this one. So what should you be able to do with this? Number 1, identify the VSEPR geometry for a given molecule. Justify the properties of a compound based on its geometry, including the presence of a dipole moment. Assign bond angles based on hybridization or VSEPR up to sp3 for hybridization. And that also means be able to identify the hybridization. Quantify the number of pi and sigma bonds in a molecule. Identify 2 molecules as being geometric isomers. Now, along with this identifying the VSEPR geometry, you should also be able to identify bond angles, be able to talk about bonding, non-bonding pairs, things like that. But you do need to memorize the VSEPR geometry names. And then finally, compare the bond strength of sigma and pi bonds. So that is it for today, and I will see you in class.